Good evening, everyone. This is the session 3 from the playlist of IIT JEE Advanced Part 2. The chapter is Electric Charges and Fields, and the topic is Electrostatic Equilibrium. And this is the question which I have taken for this session. This question, a very similar question was asked in the IIT JEE 1987 examination, and in that question means a question which was asked in the IIT examination. So in that question, the charge was placed at the center of the line joining these two charges. But here what I have done is I have simply manipulated this question and I have written here a charge small q is placed on the line joining the two charges. So we have to find the magnitude of the charge, that is of the charge small q, for this system of the three charges to be in a state of equilibrium. So for this system of three charges to be in a state of equilibrium, the net force on each charge due to the other two charges should be equal to 0. So this is the condition under which this system of three charges will be in a state of equilibrium. That is, the net force on this charge, that is a capital Q, the net force on this charge, that is small q, and the net force on this charge, that is capital Q, should be 0. And in that condition, this system of three charges will be in a state of equilibrium. So I am here considering that let us consider the distance between these two charges, that is distance between this charge capital Q and this charge capital Q is capital D, and I am considering the distance between the charge small q and this capital Q as small d. So now I am just taking this point as A, this point as let us say O, and this point as B. So now first of all I will be finding the for this charge to be in a state of equilibrium, the net force acting on it in this direction, that is towards this charge capital Q, should be equal to the net force acting on this charge in the opposite direction. And for that purpose, and in order to attain this configuration, this charge has to be a negative charge, because if it is a positive charge, then as we know that like charges repel each other. So because of this positive charge, the electrostatic force on this charge will be in this direction, and the electrostatic force because of this charge, that is capital Q, will also be in this direction as indicated by this arrow. So as a result, this charge will not be in a state of equilibrium. Similarly, if this charge is positive, then the net force because of this charge will be in this direction, because both are positive charge and like charges repel each other, and the net force because of this charge capital Q will also be in this direction. So the net force on this charge Q, the capital Q, will also be in this direction as indicated by this arrow, and as a result both these two charges will not be in a state of equilibrium. So this charge has to be a negative charge. This will be a negative charge, because if it is a negative charge, then these two are unlike charges and there will be a force of attraction between them, and because of this charge there will be a force of repulsion. So if this force of attraction is equal to the force of repulsion, then this charge will be in a state of equilibrium. Similarly, because of this negative charge, there will be an electrostatic force acting in this direction as indicated by this arrow, and there will be an electrostatic force acting on this charge due to this charge which is placed at A, and it will be in the direction as indicated by this arrow. So if both these two forces are equal, then this charge will be in a state of equilibrium. So now, based on this conversation, based on this idea or based on this concept, we will be now trying to first of all find the position of this charge small q on this central line. So let us consider, as I have just taken here, that the distance of this charge, that is this charge q from this charge capital Q is d, and both this the distance between this charge, that is capital Q, and this capital Q is capital D. So the force on this charge q due to this charge q which is placed at B, let us say the force on this charge, I'm just denoting this force as that is q, it is force on the charge which is placed at A due to B. This will be equal to, you know the formula for the electrostatic force, F is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R square, where R is the distance separating them. So this will be equal to, I will be taking 1 by 4 pi epsilon naught as a constant, so K, and the magnitude of these two charges R is equal to Q, so this will be equal to Q square divided by the distance between them, that is equal to D square. So this is the first equation. Now the distance between this charge, that is small q, and this charge capital Q which is placed at A is small d. So the force on this charge which is placed at A due to this charge small q which is placed at O, I am just denoting as FO, this will be equal to K Q upon D square. Okay. One thing is there that we have already identified that this charge has to be a negative charge if this system of these three charges has to be in a state of equilibrium. So here now I will be not taking this minus charge into consideration, because now I will be only finding the magnitude of the this charge q, small q. Now for the, this is the second equation. Now for this this system of three charges to be in a state of equilibrium, this FAB should be equal to FAO, or we can say that K Q square upon D square, this should be equal to K Q upon D square. So from here what I am getting one relation, that is Q square, or you can say this one will get cancelled out, that is Q upon D square will be equal to Q upon small d square. So this is the first relation, and so I will be writing this relation here, that is Q upon D square is equal to small q upon small d square. Now let us take the case, let us balance the forces on this charge q which is placed at B. So now if this distance is d, so this distance will be equal to d minus d. Okay, so the force on this charge q which is placed at B due to this charge, that is q, small q, which is placed at O, which here I am denoting as FBO, this will be equal to K Q upon D minus D square. So this is the third equation, and the electrostatic force because of this charge q which is placed at A on this charge q which is placed at B, this will be equal to, that is the, I am just denoting this as FBA, that is force on this charge is placed at B due to the charge which is placed at A, which is equal to K Q square upon D minus D whole square. Let us say this is the equation number 4. And if for this system of 3 charges to be in a state of equilibrium, this F BO should be equal to FBA. So if I equate these two equations, that is 3 and 4, I will be getting K Q Q divided by D minus D whole square, and this is equal to K Q square divided by D minus, this will be equal to F, BA will be equal to, not the distance between these two charges is D. So this will be equal to D square. So this will be equal to K D square. So now from this equation, I will be getting, for what this K and K will get cancelled out, Q and Q will also get cancelled out. So I am getting Q divided by D minus D whole square. This is equal to Q upon D square. Now from this equation, that is Q upon D, the capital D square is equal to Q upon, that is small q upon small d square. What I will be doing is, I will be substituting the value of this Q upon D square as Q small q, that means this is equal to Q upon D square. Here capital Q upon D square is equal to Q small q upon D square. So I put the value. So this equation can be also written as Q upon D minus D whole square, that is equal to Q upon capital Q upon capital D square. This is equal to Q small q divided by small d square, because capital Q upon capital D square is equal to small q upon small d square. So from this relation, from this relation, that is from this and this, I will be getting Q D minus D whole square is equal to Q divided by D square. So this Q and Q will get cancelled out, and finally what I am getting is D minus D will be equal to D, or 2D is equal to capital D, or we can say that implies that D is equal to D by 2. So this system, if it is a negative charge, if Q is a negative charge, then this charge has to be placed at a distance given by, that is capital D by 2, which means that this charge is to be placed at the center of the line joining these two charges. So now substituting this value, so D is equal to D by 2. So what I will be doing is, I will be using, now we know that Q upon D square is equal to small q upon D square. So now what I will be doing is, I will be substituting the value of small d as D by 2. So from here, Q is equal to Q D square upon D square, that is small d square divided by capital D square, and small d is equal to capital D by 2. So this will be equal to D square upon 4D square. What I have done is, I have substituted the value of small d as capital D divided by 2. So this is what I will be getting. So the magnitude of the charge will be equal to Q by 4. So here the magnitude of the charge is equal to Q by 4, and this would be a negative charge. So Q will be a negative charge of Q will be a negative charge of magnitude Q divided by 4. So this is the answer, and I hope you have understood the solution of this question. The only thing which you have to remember is that for any system of charges to be in a state of equilibrium, the net force on each charge should be equal to 0. So based on this concept, we were able to find the magnitude as well as the nature of the charge using this concept. So thank you very much for joining this session, and in the next session I will be coming up with a different type of a question, but the chapter will remain the same, that is electric charges and fields. So till then, have a nice day. Bye.